Okay. Thanks, Igor, for the introduction. Of course, thank you to the organizers for having me. And a big thank you to Ausra, who I don't see right now, but for putting together a really great program. The topic of today's talk is going to be teacher propagation, as you can see. And it's an obvious play on a phenomenon that you're all definitely aware of, namely error propagation. The argument being that in addition to errors that we know are very useful signals to transport through networks, there might be other signals that could be also very conducive towards improving the efficiency and efficacy of neural networks. I was very happy to see that this year's ICANN unites two communities, both the titular ANN community, but also people working on biological neural networks. And I tried to satisfy both communities in the slides to come. Speaking of these two communities, I think it's pretty clear that artificial neural networks have taken their inspiration from biological neural networks, but there is still an obviously huge gap to bridge in terms of intelligence per joule or per calorie. I'd like to dwell on one word in the sentence that I previously said, namely inspiration. When building artificial systems, I think it's important to take inspiration from the brain, but not to copy the brain. This is something that historically has happened in the community, and it's still an open question which mechanisms that are present in the brain are actually useful for computation. A few historical examples to I hope drive home the point is starting with the very, let's say, atoms of computation in these networks. Neurons and synapses in ANNs are much, much simpler than the ones that we find in biology. We have ultimately reduced these complicated things to units that do sums and products, essentially. The same can be said about convolutions, clearly somehow inspired by the spatial, topologically structured spatial receptive fields of cells in the visual cortex. But it would be hard to argue that in biology you find exact copies of the convolutional kernel between neurons. And finally, maybe a more recent example, attention. I think there the inspiration is, if any, only loosely based on psychology, because clearly the mechanisms that we find in transformers are definitely not directly copied from things that we find in the brain. So one essential ingredient in the, what would you call it, deep learning revolution was the emergence, in this case, it's probably fair to say somewhat serendipitous, of hardware that is capable of carrying out very effectively the operations that are at the core of these networks. However, I would argue that this hardware is still pretty far away from what would be optimal. So the thing that I would like to argue for is the notion of physical computation, where the physics of the device that does the computation is as close as possible to the mathematics that you would like to carry out. And this is an example that I find very compelling. What you see on the top, some of you might know this schematic. It's a circuit for adding two 3-bit numbers. I hope you appreciate the complexity despite this relatively simple operation. The alternative would be probably the simplest electrical circuit that you could imagine. If you just pass a current through a resistor and you can control these two variables, then in order to carry out the multiplication, you simply need to measure the voltage that spans the resistor. So this would be an example of having the physics of your system very closely implement the mathematics that you care about. This is the case for many systems for many devices, for example, in the world of neuromorphics. This is an example that I'll come back to later. This is just a teaser. The point being that even with relatively small, simple chips designed by groups of researchers, it is possible to rival the state-of-the-art set by, for example, NVIDIA. Now, when you talk about physical learning, as opposed to learning on off-the-shelf, let's say, von Neumann architectures, there is one big caveat, namely the fact that all of your operations need to be local. So you need to have the signals that you care for in your mathematical operations at the locus of the components that actually carry out this operation. So this is something that many people describe as in-memory computing. There is a huge benefit to this, of course, because if you're able to do that, you avoid the von Neumann bottleneck, which is probably the main contributor to the energy waste in modern computational systems. So in this case, the credit assignment problem becomes an even more complicated credit transport problem. How do you get the credit to the synapses, for example, in your system? And this brings me to the first part of the talk, where I'll talk indeed about error propagation through both space and time in physical systems such as the brain. I think you'll appreciate in a moment why the crystal ball is symbolic for what we need to do. So, as a simple sort of boil down the question of propagation through space and time to the simplest case, imagine 3 neurons in a brain that are connected in a feed-forward fashion. And these neurons have dynamics. They are, to some extent, slow, so it takes time for information to propagate from the first to the second to the third neuron. How would you assign credit to the synapse at the bottom for what the neuron at the top is doing? One way, and indeed the way in which most people do it nowadays in deep learning, is backpropagation through time. This is a variant of the more general class of future-facing algorithms. And the way you do it is you forward propagate all the activities in the network until the very end. You store them. And when your simulation ends, you calculate the errors at the topmost neurons, and then you unroll the computational graph and you backpropagate them through space and time. And the key word here is running your simulation to the end and then unrolling towards the past. Clearly, this is a highly non-local operation. It violates causality. So this is something that is quintessentially offline. This is not what might be going on in the brain and not something that you want in an efficient online learning system. A class of algorithms that is much less well-known, and to be clear in a moment why, are past-facing algorithms, such as real-time recurrent learning. The idea here is to forward propagate not just the activities, but also the local gradients at every point in time. These are these M objects over here. These are three-dimensional tensors. They describe the effect of synapse JK on neuron I. So you can already see from this list of indices that these are non-local objects. They connect something that lies somewhere in the network with something that lies somewhere completely different. So it's non-local in space. And in particular, the reason why nobody uses it really nowadays is that it is very memory hungry. So it scales with the fourth power of the number of neurons in a network. Clearly, as your networks grow big, this is something that is unsustainable. So neither of these algorithms satisfy the need for locality that I mentioned before. Let's take a step back and do what physicists like to do and build a theory of backpropagation from tabula rasa. And another thing that physicists like to do is talk about energies of a system. The reason being that if you are capable of describing the energy of a system at any point in time as a function of its state, you are done. From that, you can derive all of the dynamics of the system. The energy that we propose has quite an intimate relationship to a sort of energy that is already used in deep learning, named the loss function of a network. The difference being that the loss function only operates on the output neurons, whereas the energy is a measure of the entire system. And just to remind you of our goal, ultimately, we want plasticity to be described as a local thing, in particular local gradient descent. So the synaptic update, the update of synapse ij at the time t, should only depend on quantities at the time t that have indices I and j, so that are adjacent, that are physically adjacent to that synapse. To give you an intuition about what this energy represents, it is sort of a measure of the internal frustration of the system. So the beta in the equation above represents the influence of the external signal, of the teacher, if you will. As beta is 0, there's no external influence. The network essentially doesn't know whether it's right or wrong. It's happy, so the energy should be 0. There is no internal frustration. Now, as you slowly drive up the influence of the teacher, you generate a non-zero energy landscape along which the dynamics of the system simply evolve. It evolves on this sheet or on this manifold. And what learning does is it pulls on the state of the system at every point in time. So it pulls on this manifold until hopefully at the end of learning, the system is again moving in a zero energy manifold, but this time while the teacher is present. So it starts doing what it's supposed to do. As you'll see in a moment, the equations that we derive are based on a generalized form of conservation of this energy, which is also familiar from physics, which is why we call this approach a generalized latent equilibrium. So more precisely, what would this energy look like? The equation looks a bit scary, but it's relatively simple. It's a sum over neuron local energies. And this is the membrane potential of a neuron. And these are its bottom-up inputs. So this neuron local error is simply the difference between what a neuron wants to do and what its bottom-up presynaptic partners think that it should be doing. And with this, as promised, we are done. So from the energy now, we can derive all the dynamics of the network. This is the generalized conservation law. The details maybe don't matter so much, other than the fact that the change of the energy with respect to the variables is 0. So this is where you see the conservation. And now you can just, as you say in quantum mechanics, shut up and calculate. You do the math, and what comes out is an equation that should be familiar to most computational neuroscientists. It's the one over here. And this just tells you that a neuron is a leaky integrator of its inputs, plus this term over here that we'll come back to in a second. So already we rediscover something that is well known. This is a good thing for a theory. I would like to add that this equation already suggests the compartmentalization of neurons into several pieces. It seems to be useful for the membrane of a neuron to actually hold 3 pieces of information, something like a somatic potential, a basal potential, and an apical membrane potential. And this indeed is already a step into the direction of the complexity that we observe in biology. So this could be a good argument for why the neurons, the pyramidal neurons in cortex, are structured the way they are and not in a different way. And now we finally derive the thing that we wanted to achieve, ultimately, the dynamics of parameters, so the learning rule. In this case, for synapses, you can do it for all parameters as simple gradient descent on this energy. And what you get is a local rule by virtue of the locality of the energy. And it's just the synaptic update is just the product of the postsynaptic error and the presynaptic rate. Now we come to the error term. What does the error term look like? And I hope many of you will recognize at least the internal part of this equation, because this is the backpropagation equation through space. And the stuff that's on the outside, it's a bit more complicated, but it's an approximation of error backpropagation through time. How do you get this locally into your synapse? Through a circuit. So this is a circuit diagram that we propose for error backpropagation through space and time in cortex, with pyramidal layer 5 neurons transporting the signal or the information upwards through the hierarchy, and layer 2-3 pyramidal neurons transporting the error backwards with lateral interaction. For those of you who are maybe less interested in biology, you can strip away all of the biologically sounding words, and what you are left with is a simple circuit diagram. So this is something that you could directly cast into silicon and is capable of local error backpropagation. Now, this is not just nice math, but it's also useful in practice. What you can do is you can take these neurons and these microcircuits and put them together into hierarchical networks. What ultimately results from this is a type of spatio-temporal convolutional networks. So each neuron has sort of pays attention to a topologically local volume of space-time. And this attention window can be learned through plasticity. So here are some results on temporal data. For example, Google speech commands. As you can see, these networks are competitive with their state-of-the-art deep learning correspondence, things like temporal convolutional networks or GRUs or LSTMs. And as I just said before, these attention windows can be learned. So with the very same network, you can go from analyzing speech to classifying images. The networks will simply learn to pay attention not to the past, but simply to the present. Again, with competitive performance on datasets like CIFAR, or if you prefer to classify, to find Higgs bosons in data from the LHC, you can also do that. For more details, you can take a look at Federico's poster later today. And I'm sure you will learn much more than I was able to convey in these couple of minutes. Coming also from the realm of neuroscience, we're also somewhat forced to ask the next question, because we know that neurons in the brain don't have these smooth activation functions that we're used to from ANNs. So they don't have these, what we would call rates, but rather they spike. So, and this, by the way, is also the case for neuromorphic platforms in general. So if suddenly your activation function changes from a smooth function to a spike, that seems to present a problem, because the nice and smooth energy landscape that I've shown before actually now becomes jagged, because these delta functions are actually singularities. So it becomes, at least apparently, difficult, if not impossible, to calculate gradients. One way to recover your ability of calculating gradients is to simply use approximations. So you approximate these singular activation functions by more smooth versions, and these are called surrogate methods. They work very well in practice, but I would say that they don't really address the problem, which I would argue is actually a non-problem if you think a little bit more about it. Because if you look at the activity in a spiking network and what the spikes might be encoding, it's probably, or almost definitely, not the fact that the neuron spikes, but rather the time of its spike that conveys the information. So what we are interested in is not changing the spike, but rather the time at which the neuron spikes. And of course, now, if we consider how the output spike time relates to input spike times, suddenly this becomes a continuous function of parameters such as weights and delays in the network. So now we can calculate gradients, and we can write down a computational graph. So we can just essentially create a piece of software that does all the propagation through spike times, not as an approximation, but as an exact result. And we can take this now to neuromorphic devices, for example, to apply to concrete problems, classifying, for example, handwritten digits in this case. I hope that you will appreciate the apparent noise in these traces over here. So these are traces recorded on one of these analog devices. And despite the noise, the uncertainty in the signal, the algorithm is capable of reliably producing the correct output. And not only that, but two important points here. First of all, due to the specifications of, or by design basically, in the construction of the system, the dynamics of these neurons are particularly fast. They are accelerated to several orders of magnitude compared to neurons in the brain. So we are capable of classifying the full MNIST dataset. The reason why we chose MNIST is simply because of the size of the system. So 10,000 samples classified not in parallel, but sequentially, one after the other in less than a second on this system, with less than 16 microjoules per image. So for the biologists in the room, banana for scale, that corresponds to 30 billion classifications on the energy budget of a banana, approximately. For those of you who are more into deep learning, this has rivaled the performance of an NVIDIA GPU at the time. And as I mentioned before, most people concentrate on learning weights in networks, and that is great. Turns out, though, that delays are also important parameters, and they can be learned exactly. And whenever you have access to both weights and delays, you can improve the performance of your networks compared to the situation where you only have access to the weights. And this is a more recent result. This is mainly for the computational neuroscientists in the room. We also looked at the emergent structures from this type of learning in spiking networks. And we observe two things that are very reminiscent of something that you can observe in cortex, for example, in visual cortex. One is that as activity propagates through higher cortical layers, and I'm sorry, the higher layers are actually on the bottom, so it goes from V1, V2, V4, etc. This would be the equivalent. The activity is first spread out over time, but then bunches together in tight pulses. So you observe a synchronization of spiking activity. And the second thing is that the populations of neurons that fire become more and more linearly separable as the activity goes up the hierarchy. So this, what we would call semantization, so the clustering of activity by meaning of the input, is also something that you would observe in cortex and that is also predicted by other theories. So this concludes the part on error propagation. And now I'd like to move on to propagating other types of useful signals. And staying with spiking networks, again, taking a step back and considering what our brains actually need to learn. I think it's relatively sensible to argue that what we need to learn is not a fixed picture of reality, but rather a probability distribution over all plausible realities. The reason is that, of course, our knowledge of reality is limited, our senses are noisy and definitely incomplete. So I don't know what's happening outside of this room, but I can imagine many scenarios, all of them being realistic. So they all contain humans, but hopefully none of them contain unicorns. A question now appears, if we want to represent probability distributions, how do we do that? There are several ways of doing that. And now we can go to psychophysics and find out what the brain actually does. And this is an example of a bistable image. Some call it an optical illusion. I'm sure you're all familiar with it. So what you see is either a duck looking towards the left or a rabbit looking towards the right. I'd like to stress the fact that you can never see the duck and the rabbit at the same time. So you see either the duck or the rabbit. The same is true if you consider imagination. So whether you close your eyes and think about what's going on in this room, or when you're dreaming, you're not representing multiple scenarios at the same time. And you're also not representing probability distributions explicitly, but rather you are going, if you will, reality by reality, sample by sample. And this brings me to the argument that I'd like to make ultimately, that what the brain apparently does is representation of probability distributions by sampling. So you go duck, 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 and suddenly your perception changes, and then you see the rabbit, 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 and then you switch back. And by gathering samples from this bimodal distribution, you increasingly represent this distribution more and more correctly. This kind of sampling, which is more technically speaking, Markov chain Monte Carlo sampling, as many of you know, has quite a few applications outside of brain science. One surprising one might be quantum tomography, and I'll come back to that in a moment. So very briefly, what does sampling have to do with spiking activity? It turns out that if you look at the spikes in the brain in a certain way, you can map this activity to a binary vector that evolves continuously over time. And as soon as you have a binary vector, you're thinking immediately of Hopfield networks and Boltzmann machines. So there is a tight equivalence between these systems. And indeed, it turns out that in the cortical so-called high conductance state, so the state in which arguably we are doing our reasoning most of the time, the probability distribution that describes these spiking states is actually Boltzmann. So if we know this, we know how to learn this distribution. We simply reduce the Boltzmann energy. And in order to do that, we need to propagate, in this case, correlations. So this is the wake-sleep algorithm. It translates to a local Hebbian learning rule. And what we can get from here are networks that are simultaneously generative and discriminative. Again, just a toy example, you can see a network that has learned to dream about handwritten digits and classify them at the same time. But as I mentioned before, this has also concrete applications outside of neuroscience. And here is a somewhat serendipitous example that we came up with because our colleagues doing quantum tomography were basically sitting next to us in the institute. And we can use the neuromorphic systems that I just mentioned before. So this is the brain scale system from Heidelberg. In order to do the sampling, because it is so fast, it can gather samples very quickly, so it can approximate the probability distribution very quickly. Now, what do probability distributions have to do with quantum systems? Well, you probably know that a quantum system can be represented by a wave function, but there is an alternative representation by a so-called density matrix. This is a complex valued matrix, but there is an exact mapping from this complex valued matrix to a real valued matrix. And as soon as you have real numbers, you can represent them via probability distributions. So now you have the complete mathematical chain from probability distributions to wave functions. And here's an example of a representation of a quintessentially quantum mechanical system, a so-called Bell state, with these neuromorphic systems. So you can reproduce quintessentially quantum mechanical phenomena that are not there in classical physics. And to take this one step further, I mentioned the acceleration factor of these chips in Heidelberg that are based on conventional CMOS. But if you go from electrons to photons, you can increase your computation speed again. So you can use semiconductor nanolasers to replicate the spiking behavior of neurons. And now, if you think about the timescales in biology, you have timescales of milliseconds for the evolution of membranes. In the hardware over here, you have timescales of microseconds. And now, in the nanolaser system, you have timescales of nanoseconds. So this might be the future of fast sampling. One last detail about these systems, again, taking inspiration from biology, to answer the following question that might also be familiar for you. If you have such systems that you train by contrastive means, what happens very often is that the probability, that the troughs in the probability landscape or the energy landscape, it's the same thing, become very deep. So the system is stuck in local states and cannot leave them. And there are actually two mechanisms that are ubiquitous in the brain, namely short-term plasticity and oscillations, that are helpful in solving this problem. The way you can imagine this is that short-term plasticity increases the height of the local energy trough, so it literally throws the system out of where it is right now, allowing it to travel through the energy landscape. What the cortical oscillations do is a form of annealing and tempering. So by oscillating, they regularly squash the energy landscape. It's a form of tempering or annealing, if you will. And again, this makes it easier for the system to jump out of local energy minima. And you can see how, in this case, we trained the networks on a bunch of images of children's toys. Without oscillations, the system is stuck. with oscillations, it travels nicely through the landscape of available images. Now, I have to admit that until now, I have told you a little white lie. It was a lie by omission. There is one thing that is still missing for full locality in all of these systems, which is this thing over here. Many of you, I'm sure, are familiar with this. This is the weight transport problem. It's something that you don't care about in machine learning, but that you care about a lot in physical systems such as the brain. So, briefly put, in the propagation of errors, you need to know the weights of the forward propagation of signals. So you need to transport the weights from the forward stream into the backward stream. One solution, let's call it, to this problem is to ignore it. You can just say, okay, we use a random matrix for backpropagation, and then while adapting the forward weights, we hope that they will at least to some extent align to the backward weights and that the gradients will be useful. This is true. This is called feedback alignment. I would say it's a bit of a misnomer because the feedback is actually constant. Nothing is aligned in the feedback. This works well for shallow networks. As soon as you go a bit deeper, this fails, because every time you turn the gradient a little bit, at some point you'll turn the gradient by more than 180 degrees, and then you'll evolve into the wrong direction, basically. So what we need is true alignment learning, or you might call it actual feedback alignment. So a thing that you would want to propagate through these networks now is their symmetry, or rather the asymmetry between the information streams in order to ultimately achieve symmetry. And we have two approaches for this, one in rate-based networks, one in spike-based networks. The first one is called PAL, phaseless alignment learning. It's phaseless because it happens at the same time as forward learning. There are no phases in the system. Both streams learn at the same time. I will not go through all the equations. I'd like to just give you the intuition of how this works. And the main mechanism on which this is based is noise. And now we know that you get noise for free. It's ubiquitously present in the brain. And it's also not so hard to engineer hardware systems that contain a reasonably small but non-zero amount of noise. So if you consider the forward and backward synapses in this little network, if you have noise over here, this noise gets transported through the forward synapse to the next neuron, and then the noisy signal arrives at the backward synapse that lies, I mean, here it is at the distal site, but you can consider that it lies proximally to this neuron over here. So the backward synapse has local access to the original noise and to the noise that has been transformed by the forward synapse. So by comparing these two signals, it can recover the effect of the forward synapse and thus also recover the forward synaptic weight. What you can do technically, if you like energies, as we do, is to add another term to the energy function, and then again you can calculate everything nicely from the energy as a gradient. And what you can prove mathematically is that the backward synaptic weight vector learns to approximate the forward synaptic weights. It's actually the Jacobian, but we can go into more details later. This doesn't only work well in theory, but it also works well in practice. So if you look at the alignment between forward and backward synaptic weight matrices over here, you see that they go nicely, relatively close to zero. So the synapses are well aligned, and this also translates into an advantage in terms of functionality. So networks endowed with this kind of alignment learning perform better than networks that do not have this alignment mechanism. As I promised, there's also a spike-based version of that. And it is again based on noise, and it is again based on symmetry. So if you consider a pair of neurons that are symmetrically connected, and you look at the spike timing, their relative spike timing, because of the symmetry, you would expect the same amount of pre-post spike correlations as post-pre spike correlations, right? The neurons are exchangeable because everything is symmetric. So you would expect a flat curve, this black curve over here. But now, if one synapse is stronger than the other, you would expect more correlations of pre-post type than post-pre. So you would see that suddenly the spike time distribution becomes asymmetric, especially around the center, but not only. So you can guess where this is going because I talked so much about spike timing. How do you recover symmetry in the system? You can just do this by looking at the relative preponderance of spike timing in both windows. This can be achieved by spike timing dependent plasticity. So you just need an STDP kernel that, unlike the classical Hebbian kernel, is anti-symmetric. So it punishes synapses that are too strong in one direction and it strengthens synapses that are too strong in the other direction, ultimately recovering symmetry. So you see this nicely in these trajectories. You start out at some point in synaptic weight space where the synapses, forward and backward synapses, are different, and then their weights nicely evolve towards this diagonal. So the stable manifold of these dynamics is the diagonal, which of course is the locus of equal synaptic weights. This also works in deeper networks. You can see here nicely the alignment of forward and backward weight matrices in multilayer networks. Not only does this allow you to essentially recover the performance, this is the distance between the target activity and the actual activity in the network. So you recover the performance that you would have with perfectly equal synaptic weight matrices. And also this works for increasing amount of noise. So as you increase the asymmetry between synapses, you see that the accuracy of the system drops. But with spike-based alignment learning, you recover the baseline for equal weights. This is also something that we are presenting in one of our posters. In particular, Timo, who is here, will have a poster on SAL later today. So if you want more details, I'm sure he'll be happy to tell you more. As a final point, I'd like to talk about, again, not errors. So everybody's a big fan of errors for good reason. But we have wondered whether this is really the go-to method of learning in general in recurrent networks. And we found out that actually, especially in smaller networks, it turns out that there might be an easier way to do things. And to propagate, instead of propagating errors, to actually propagate teachers. I'm avoiding the term targets because there is a thing called target propagation, and that's not what we're doing. To propagate teachers throughout the networks. To give you an argument for why we even consider this problem in the first case, this comes from how to train and to apply recurrent networks for practical problems. A big topic in recurrent network learning is reservoir computing. It has been for quite a while. For those of you who aren't familiar with reservoir computing, essentially you don't learn the synapses in your network. What you only do is you train a readout. Your network does whatever it does. It projects your input activity to some high-dimensional space. Hopefully there it is more linearly separable, and then your output layer can do the job. The problem, the well-known problem with reservoirs is that they don't scale really to more complex problems. So in order to attack a slightly more complex problem, you need to increase the size of your reservoir a lot, if it's even possible at all. And this is also a problem that has plagued the neuromorphic world because many people in neuromorphics actually like to use reservoirs, especially those people working on new physics, because when you build a new device based on whatever, memristors, photonics, skyrmions, it's difficult to control. So what you like to do is just look at what the system does, train a readout, that's your reservoir computing. There are ways to do efficient local learning in recurrent networks as well. I'd like to mention two here, Follow and especially Force. I guess Force is the more famous one. The problem with these approaches is that they also require assumptions that are either difficult to put into practice or non-biological, for example, the presence of a global error signal, or in the case of Force, synaptic dynamics that are much, much faster than membrane dynamics. What we propose to do is to build networks out of these relatively simple components that you have already seen before at the beginning of the talk, namely multi-compartment neurons. So we just need neurons with two compartments, a somatic compartment and a dendritic compartment. And the learning rule for the synapses on the dendrite is similar to the one that I have talked about before in the context of error propagation. But what the synapses do is they simply try to change the activity of the dendrite in order to better and better approximate the activity of the soma. So essentially, you have the teacher at the soma, and the students on the dendrite try to mimic the teacher. This is why we call this essentially teacher propagation. You'll see in a moment what propagates. Now, how to set up these networks, and also the general biological inspiration for what we did here was learning by mimicking, and one particularly let's say, simple and obvious example for that is the way zebra finches learn, where the male young birds learn the songs that they sing. It's actually one song that they learn from their fathers. So we wanted to mimic and possibly to explain this kind of sequence learning. In order to do that, we started with a tabula rasa network, a network of neurons that are at the beginning unconnected. There are two populations of neurons, a visible and a latent population. And now we mimicked something like the developmental process in the formation and development of embryos, where you start out by connecting these neurons with a sparse somatosomatic scaffold. So synapses from the somas of neurons to somas of other neurons slowly spread throughout the network. And this is the teacher network. So these are the synapses that propagate the teacher signal throughout the network. And then you have a more dense matrix of somatodendritic connections, and these are the synapses that will ultimately learn. And now we can put this to the test. We can let it learn a song. In this case, it's not a bird song, but it's Für Elise, so you probably recognize the pattern over here of Für Elise. You can map these activations directly to the keys of a piano. And throughout learning, throughout this kind of teacher learning, you see how the latent layer starts generating activity patterns that are maybe unrecognizable to us, but that ultimately help in sustaining the target pattern or the teacher pattern in the visible layer. What I'd like to draw your attention to in particular here is the y-axis of these plots. The number up here is 40, so the number up here would be 50. We can learn the first phrase of Für Elise with really tiny networks of, if you take the sum of neurons in both layers, something like 70 neurons or less. And in particular, this is something that is impossible for reservoirs to do at this size. So you would need much larger reservoirs to learn these patterns, if it's at all possible, because these are quite non-Markovian. So you need to remember the past in order to produce the next tone. These networks are capable of learning, of course, many different patterns. Here's a set of Bach preludes learned by these networks. They can learn patterns of varying output intensity. They can also learn to extract information from noise. So if you present noisy patterns, then the networks will extract the pattern that lies behind the noise. And again, if you want to learn more about what we did here, please take a look at Ben's poster later today. And this brings me to the end. Again, thank you very much for having me, and I'm happy to take your questions.
Okay, thank you very much. Questions, please?
Yeah, I wanted to make a general comment to what you first said, inspiration, one can draw from neuroscience. That is, of course, has been true in the beginning, and a lot of inspiration has been drawn from the neurosciences. But now the neurosciences started out as a science intending to understand the human mind, but they have given up on that goal, as we all know. It's becoming essentially a biological science, and progress in understanding the human mind in the last 20 years has essentially been nil. On the other hand, machine learning has come up with hypotheses which probably would help us to understand the brain. Take, for example, attention mechanism. Both in psychology and in the neurosciences, essentially we have a descriptive view of attention, but there has never been an algorithmic possible implementation. And normally the view is you do first model, you first learn the world. You know, for example, about yellow and green, and then you can have attention on green objects. And machine learning says this is essentially wrong. You have to learn both together, the world modeling and the attention mechanism. And that is, for example, a lesson or a hypothesis. We don't know whether it's true in the brain or not, but a hypothesis which works in machine learning application millions of ways that we have learned both together. And there are more of these examples, like chain of thoughts, built on information bottleneck principles. So machine learning has come up with many hypotheses which probably should inspire neuroscience and probably lead to more progress understanding the human mind than the other way around now in the last 10 years.
So I missed the question mark at the end, but I very much agree with your comment. So I think this goes back to what I said at the beginning, right? Just to some extent. So while machine learning has clearly taken inspiration from the brain, it has diverged, and it is not the case that everything that machine learning is finding to be useful is necessarily also something that is present in the brain. However, I think about attention and the specific structures that we have in transformers, we can argue, but something that is definitely present in the comp neuro community is error backpropagation, the thing that I talked about in the beginning. Clearly, this is inspiration going from machine learning to neuroscience, actually against the pushback, the initial pushback from neuroscience. So there are these famous statements by people saying that error backpropagation in the brain, when was it, in the 80s, is impossible, right? And nowadays, we find solutions not only for backprop through space, but also backprop through time. So yeah, in this sense, I agree.
So it's somewhat connected to the previous question. Do you think that neuromorphism can be fully reduced to spikes? I mean, is there anything in three-dimensional organization of the neurons, topology of their connections?
So I have to be careful what I say here, not to offend my neuromorphic friends. I also come from that community, among others. I think that having spiking systems in order to understand the brain better is a worthwhile effort. The brain is spiking. But then already here we get into more complicated territory, because the standard model that is used in neuromorphic devices is leak, integrate, and fire. Now we know that the brain is capable of producing much more complicated patterns. So you can say, okay, then you could do something like adaptive exponential integrate and fire, but this still is missing a lot of stuff, such as plateau potentials, for example. I should raise the flag for our colleagues in Heidelberg who have put great efforts into implementing all of these mechanisms into the hardware. So on the brain scale system, you do have adaptive exponential integrate and fire neurons, you have a form of plateau potentials, etc. But still, I think there's quite some complexity missing. Now, having said that, if you want to have practical applications, so if you want to harness these systems for doing things in the real world, then I think that trying to slavishly copy the example of the brain only holds us back. And machine learning is a clear example of how to do it differently and how to do it well. So while I think that spikes are a good idea in the sense of not having time continuous exchange of information between your variables, but rather sparse in time, which makes it more efficient, restricting yourself to a 1-bit code, essentially, even if spike timing helps there, is a big restriction, and we should learn to avoid it in the future.
I'm afraid we have to stop because we're delayed. So I believe that Mihai will be around during the today.
At least today.
So at least
but,
today. So
these guys are around for longer, so and they are very knowledgeable. So ask them all the questions.
And you can talk the poster stands to students or colleagues, right?
And tomorrow and the day after tomorrow.
All right. So thank you again.